Hi guys, I'm Mithila and I'm in Ms. Jayanti Talapathi's chemistry class. And so today we're going to be doing a seminar on the ideal gas law. Okay? So this is me, Mithila, and these are my friends. This is Harish, this is Nazira, and this is Dashni. So yeah, first of all guys, let's begin by just defining some basic terms. So would anyone like to volunteer about what pressure is?
Force by unit.
Okay, yes. Pressure is defined as a force over a unit area, and volume.
Space.
Correct. It can be considered as the amount of space anything occupies. And the number of moles?
Quantity.
Quantity. Yes, the quantity of any substance. And temperature?
Temperature is
Heat change.
Heat change.
the heat measure.
Yes, it's the measure of heat energy that a substance uses. Yes. Yeah, so now that we've defined these four basic terms, so we're going to be looking at them in context to the ideal gas law, and we'll study the relationship between the different variables. Okay, so let's take them individually, and first do the first. First, let's look at the relationship between pressure and volume. So this is actually a very simple and intuitive experiment. Like I have this balloon, and then so there are a bunch. It's filled with air. So I have a bunch of air particles bouncing around, and the air particles, they exert a force on this balloon, and that force is greater than the force that the atmosphere exerts on it because the balloon stays inflated. So now let's say that I take one of these variables, volume, and I change it. So when I try to compress the balloon, suddenly the collisions are a lot more frequent. The particles start bumping against the walls of the balloon a lot more often. And if I keep decreasing the volume enough, the pressure in the balloon is going to be so great that it's going to burst. So here, can anyone tell me the relationship between the two variables? Like what did I decrease and what did I increase, and what decreased or increased as a result?
Increase the pressure and the volume decrease.
No, I changed the volume. So what did I do to the volume? I decreased the volume, and that led to an increase in pressure. Yes. So a decrease in volume leads to an increase in pressure. And the same would be true for the opposite. Like if I were to somehow stretch this balloon, suddenly the collisions are a lot less frequent, so then the pressure goes down. So yeah. So we've just established that pressure and volume are inversely proportional, meaning when one decreases, the other one increases. So to better visualize this, PV is equal to a constant. Let's just imagine we have a graph. X-axis, we're going to plot 1 by volume, like reciprocal of the volume, and here we plot the pressure. So this is what the graph would look like. As the 1 by volume increases, pressure also increases. So then if we were to calculate the slope would be just the change in y by change in x, right? Change in y by change in x, right? So pressure divided by 1 by volume, which is equal to PV, which because this is a straight line and not a curve, the slope is constant throughout. So that would just be equal to a constant. So this very, very simple and intuitive idea is what is known as Boyle's law. Yeah, and Boyle's law, when it's coupled with two other very important and very basic laws, actually to be frank, is what lays the foundations for the ideal gas law. Okay, so now let's examine two other variables and the effects they have on one another: volume and temperature. So can any of you guess whether they're inversely proportional or directly proportional? Just hazard a guess. Directly proportional, yes, exactly. And why do you say that? It's simple, common sense. It's just when solids expand on heating, right? So when you heat something, the volume increases. And why is it that the volume increases?
Because more kinetic energy. So
Say
more kinetic energy gained by the molecules, right? So
Yeah.
they'll be hitting towards the walls of the ring.
Exactly. So volume and temperature are both directly proportional. So as you increase the temperature, the volume increases as well. And remember, when we were doing Boyle's law or Charles' law, the other variables are being held constant. Pressure and the number of moles are being held constant. Okay? Just as how in Boyle's law we were holding the number of moles and temperature constant. Okay. So yeah, Charles' law is pretty simple and very basic. Avogadro's law is just as simple. Okay. Avogadro's law is basically self-explanatory. Basically, as you increase the number of moles, the volume increases as well. You have more substance and therefore it takes up a larger volume. So to demonstrate it, I'll call Nazira. Yeah, so right now, Nazira just filled the balloon with air molecules, and these air molecules are all bumping around and they're exerting a pressure, and they're giving this balloon a certain volume. Now, as Nazira tries to blow in more air molecules, basically she's increasing the number of moles of air that the balloon contains. The volume increases as well. You just have more substance, so therefore it takes up more space. That's all that Avogadro's law basically states. So hopefully you recognize this from the beginning of the video. It's Boyle's law, stating the pressure and volume are inversely proportional. Now when we were discussing this law, we were only taking these two variables into account, and everything else, that is the number of moles and the temperature, were all being kept constant. So now we're going to relate this equation to the ideal gas law, which states that PV is equal to N, R, and T. Now this probably looks a little fancy. I mean, it's not as intuitive as this would be, but then let's just kind of think about it for a minute. So P into V is equal to a constant, right? And we were keeping N and T both as constants. So N into T would also give you a constant. So we can safely take these two variables and plug them in here. And the product of pressure and volume is related to the product of N into T by another variable, a constant, known as R. So yeah, this is still equivalent to the earlier Boyle's law that we saw. Like all of this still sums up to give you a constant. And the cool thing about this is that you can like literally rearrange the variables to get Charles' law and Avogadro's law and still have a constant on the left hand side of your equation. So like if I were to take volume by N and then take P this side, R into P into T would still give me a constant because I kept both P and T constant during Avogadro's law. So yeah, hopefully you enjoyed this video, and that was a bit illuminating as to the origins of the ideal gas law. And yeah, thank you.